Okay, so let's get started on this one. We'll start with our ice table and fill in some things here. So these are all aqueous except for the water, so this plus this is in equilibrium with the sulfite and the hydronium ion. Again, we're working in molar concentrations. And here, remember that our initial concentrations are going to be the equilibrium concentrations from the first deprotonation. So this is the equation for the second deprotonation. And we can expect, as we did before, some forward progress for this process based on the fact that there's no sulfite to start with. So we can expect at least some forward progress, which means we're going to lose some hydrogen sulfite. That change, we'll call this X. And the other thing that gets asked once in a while is that this is not the same X as the previous slide. This represents a completely different quantity. That being said, we'll have 0.084 minus X molar hydrogen sulfide by the time this second deprotonation is done. We'll have X molar sulfite, and we will have 0.084 plus X molar hydronium when we're done. So we're taking away a little bit of the hydrogen sulfite, and we are adding a little bit of the hydronium. So the Ka2, hopefully writing these expressions is getting second nature to you. So we've got sulfite concentration times the hydronium concentration divided by the hydrogen sulfide concentration. We're going to plug in our symbolic values here. So we get, so again, this is from the sulfite, from the hydronium, 0.084 plus X, 0.084 minus X. And that is equal to Ka2, which we're told was 6.4 times 10 to the negative 8. And now, because that K is actually quite small, we can now assume X is small because of that, which makes what seemed like a fairly horrific polynomial equation actually pretty straightforward. Because we're going to assume that this X is much smaller than 0.084, which means that this Ka2 is going to be equal to approximately X times 0.084 divided by 0.084. The 0.084's cancel, so we get the interesting result that X is actually equal to, numerically, Ka2, which is 6.4 times 10 to the negative 8. I always thought that was an interesting way that that kind of, rolled out of the math here. So we have essentially 0.084 molar hydronium, 6.8 or 6.4 times 10 to the negative 8 molar sulfite, and essentially 0.084 molar hydrogen sulfite. So one thing to keep aware of is that the concentration of these two species, which were theoretically reduced in this case and increased in this case, were not changed by an appreciable amount. So again, if you're following sig fig rules, there is no difference. So these are essentially unchanged, and we're calling this a change because, well, it's still a big change from 0, but again, still a relatively small amount. And this is pretty much how you work through a polyprotic acid, in this case a diprotic acid, question. So to wrap things up and review, our sulfide concentration was about 6.4 times 10 to the negative 8 molar. Our hydrogen sulfite was 0.084 molar. The sulfurous acid was 0.416, and the hydronium concentration ended up being about 0.084 molar, which means that corresponded to a pH of 1.08. So to wrap up the generalizations of the polyprotic acids here. And so I've got the generic equilibria written down here. Maybe I should actually write them as proper equilibrium arrows that show the first deprotonation and the second deprotonation. So, and you know, the take-home lesson, so as long as Ka is a lot bigger than Ka2 by a factor of 1,000, and this is almost always the case, and that Ka2 ends up being quite small, that the hydronium produced from the second or any further deprotonations, third, fourth, fifth, or whatever, is quite negligible, and that all of the hydronium pretty much comes from the first deprotonation. And as long as Ka2 is pretty small, it'll work out that the concentration of the second conjugate base, this A2 minus here, is going to be numerically equal to Ka2, which I always thought was kind of neat. Now, I do want to point out that sulfuric acid is a major exception to that. And why is it? So sulfuric acid is one of the 7 strong acids, which you should know, which means that Ka1 is way, way, way larger than 1. But Ka2 is actually pretty strong as well, and it's about, I want to say, 0.12, which means that the assumptions that made the second deprotonation pretty easy for us aren't. Don't apply for sulfuric acid, and you do not want to see a sulfuric acid equilibrium calculation because they're ugly. We save that for sophomores or juniors or chem majors. So that's polyprotic acids. Not too bad, I hope.